the theme of climate tech. So as you know that energy is centerpiece of everything, right? And within energy, I think it's the technology that's centerpiece of the entire energy theme. So why energy? Because energy is central to climate and carbon reduction. So things are very clear, and we have an excellent panel here today to take us through some exciting world of new and emerging technologies. And my name is Ashish Rana. I'm coming from Reliance Industries, and I'm an economist. But at the heart, I'm also an engineer because my first degree was in engineering. So technology and economics go well. And I have my co-chair, Mr. Rajesh Rawat. Please introduce yourself.
Thanks, Ashish ji. And I guess, I mean, as Mr. Ashish mentioning that the technology is at the heart and center of the decarbonization. So I'm in EY Parthenon looking after the transition technologies. And I guess, I mean, we have the illustrious panel. So I will straight away go into Mr. Nicola Hewitt, who is the AUSIA project manager. And he had been working in the company for quite some time. And he would be sharing his experience from Total Energies, that how it is making a difference using the new tech in the decarbonization space. Please.
New technologies in order to monitor emissions of methane and CO2 in the atmosphere, and this is called AUSIA. This program is run as part of the targets of methane emissions of Total Energies, which are very aggressive reductions. It works by decades. The first decade was 2010 to 2020, during which Total Energies has reduced methane emissions of 47%. The next target is 2020 to 2030, where Total Energies will reduce again of 80% more its methane emission, and internally we are talking of reaching near zero methane emission in 2030. This is very aggressive, and we have intermediate targets. This is for this year, 2025, to reach minus 50% between 2020 and 2025. And in fact, this was achieved already last year in advance, and we are really proud of that. These methane declarations are monitored as part of a program run by the United Nations, which is called OGMP, Oil and Gas Methane Partnership. During the 3 years, OGMP is judging and improving the methane reporting of all companies which are participating. And from the 4th year, you get a kind of mark which is about the quality of the methane reporting. And in 2024, for the first time, Total Energies got the gold standard, and the whole team is very proud about it. So the question is, how did we do that? Total Energies is running now a very clear roadmap on methane emission reduction, and we are displaying it on 2 levels, like is doing the OGMP. On the first level, the site level, which are the blue rectangles, Total Energies is monitoring assets with satellites, both public and private networks, and with the new technologies that I will present today, which is AUSIA, a gas analyzer mounted on a drone. Those 2 technologies are now running since more than 3 years and are really in operation.
Good morning, ladies and
The
gentlemen.
next
We welcomes you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All visitors, exhibitors and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the hall. Please take care of your belongings. Thank you.
Thank you. The next level is the green rectangles at the bottom, which are the source level. And Total Energies has engaged since September 2024 in a very aggressive program in order to tackle all the source level with a high accuracy. First, it is about fugitives and incidents, which are monitored by infrared cameras, but in addition, for which Total Energy is now running a very large investment program in IoT sensors and high sensitivity sensors, so fixed sensors that will be installed in all upstream facilities. This is 13,000 sensors that will now be installed on all E&P's assets of Total Energies. For the unburnt emissions, meaning the ones from flaring, from gas turbines, stationary combustion, venting, Total Energies is implementing predictive emission monitoring systems, PEMS, and this is currently also in call for tender. And those PEMS will able to have a continuous estimation of the methane emission for all the assets. So those are really the two new pillars that have been decided in Q4 2024 and that will complement the arsenal of Total Energies to fight methane. Now, so we will focus on the emerging technology, which is a gas analyzer, OZEA, mounted on the drone. You can see the picture on the left. This gas analyzer was developed by a university and a research center in France, and Total Energies is co-owner of this technology. It measures concentrations both of methane and CO2 at the same time in the atmosphere. The plum of emission generated by the unit is flying with the wind. So the gas analyzer will fly with the drone in a vertical cross-section downwind, and in this cross-section, the concentration of methane and CO2 will be scanned all over the place. You can see examples of operations in Denmark, in Qatar. This is now running since 3 years in all E&P affiliates of Total Energies. And it has been also demonstrated beyond oil and gas business in biogas plants in France, in power generation plants, and in landfills. So what's the outcome? The OZEA is going beyond detection. The key word is quantification. The deliverable is a mass flow rate of methane in kilogram per hour and a mass flow rate of CO2 in ton per hour. And this is really making the difference, because once the asset manager has in hand the value, the number of kilogram per hour generated by his plant, he knows he has to take an action to modify it. OZEA is also producing reports of the ratio of concentration, CH4 over CO2. This means a study about understanding how good was the combustion in the combustion unit or in the flares, and to tackle it when it's not good enough. And in addition, OZEA is able to track fugitive emission. They will be quantified, but they will not be pinpointed. OZEA will not tell you that flange is leaking. It will not tell you this instrument is leaking, but it will tell you there is a leak, how much, and you need to go with an infrared camera to find it. The technology is mainly used at site level, and this is typically offshore, to quantify the whole plant. But also we are managing to cut the panels and to segregate the main sources, and we also deliver results at source level, typically at flares, for flares and for gas turbines. As part of the reports, we also get an analysis of each flight, and this is how it looks on the right, with the layout of the plant, the wind, the concentrations of methane on the left, CO2 on the right, in the vertical plan, and the ratios between CH4 and CO2. And as you see on the maps of CH4 and CO2, we are able to cut the sources where there is a lot of CO2 with a bit of methane. At the bottom, we see another source, a lot of CO2, less methane, and on the right, we see CO2 without methane. So we are able to cut them and segregate. So operations. This started for Total Energies in 2022. We have 3 years of operations behind us with a very sharp operations ramp up. On the left, we are showing the number of days of operation. For 2024, it's preliminary figures. We will end up just below 600 days of operations. So this means it's now massive. It's no more a demonstration. It's a mandatory operation at Total Energy's operated assets every year, and even more than that, because we go back 1, 2, 3 times when there is improvements that can be illustrated. We have also proposed this technology to the strategic partners of Total Energies, and 11 major assets have been surveyed. This was, for example, Petrobras in Brazil several times, Angola LNG, Nigeria LNG, Qatar Energy, SOCAR in Azerbaijan, and many others. And this year in India, Total Energies has signed 2 memorandum of understanding, one with ONGC and one with Oil India Limited. And OSEA will be flying in India in 2025, with ONGC on the west coast in 3 sites, and with OAL in the east in the Assam region. And to finish, the project needs to sustain the growth. And this growth is sustained by an industrialization program. This was first started with the ability to operate. So this consisted in exploitation license, and now Total Energy holds this license to exploit the technology, both directly and indirectly. It consisted in intellectual property protection. And then it consists in ramping up the resources. So Total Energies has first copied the prototypes, and you can see one OSEA prototype today at the Total Energy booth in hall number 1. So these copies are being delivered, and we are in the same time doing the re-engineering of this prototype in order to be able to use an industrialized, robust gas analyzer from 2026, where we will be able to supply those gas analyzers. In terms of operations, we have a real challenge because the gas analyzer is very precise, but we need to maintain the quality of our operations in order to maintain the accuracy of the technology. So we are ramping up the number of contractors which are partners of the program. Those contractors are mobilizing drones and mobilizing pilots and mobilizing trained, qualified and audited super users of the gas analyzer in order to maintain the quality. And we also work in the same time on the next drone generation, and this means drones without pilot. Autonomous drones, meaning drones taking off and coming back on their own, only monitored by an operator behind the screen, but who is not a professional drone pilot. And we are doing that with a startup company in France called UEVIA. Lastly, in this industrialization program, we are working on the data, and we have been creating during the last year full cloud development in which we have posted our algorithms, which is now in production, and which allows us to ramp up also the workload and to produce OSEA reports fairly quickly, because now we are producing reports in less than 60 days. And as a conclusion, to finish this, Patrick Pouyanné, our CEO, is extremely committed to reducing methane emissions at Total Energies, but as well he is committed at supporting the whole industry in those reductions. Total Energies is a member of the Oil and Gas Decarbonization Charter, OGDC, and in December last year, Patrick Pouyanné, in a video, has advised the members of the OGDC that Total Energy will share the technology, should they require it, to help them track and reduce their methane emissions. And this is the case with OAL and with ONGC, which are partners of the OGDC. Thank you very much.
Thank you, Mr. Nicola. So this is quite interesting, actually, that you are able to track and monitor the emissions real time. And then, yeah, of course, quantification is the bedrock of all the next steps that you need to do in decarbonization. Thank you very much for your very nice presentation. And we are happy that you are going to implement this project in India this year. Next, I'd like to invite Mr. Sanjeev Sinha, President and CIO of India Power Corporation Limited. Sir, blockchain for energy. Who better than Mr. Sinha to unpack and unravel some of these aspects? Please,
Thank
floor
you,
is
Mr.
yours.
Raina. Good morning, everyone. Thank you for the organizers for inviting me and also accepting the paper that we had submitted. I work with India Power, but we have a partner for this project, and that partner is Huga Energy Canada, which is why the name of both the companies are mentioned here. Now, we all know that India is heading towards net zero by 2070, and we have various milestones to reach that figure. We from power industry also have our own milestones, and approximately 1/3 of the carbon emission actually comes from the power industry, particularly from the fossil power generation. And therefore, it is imperative that the power generation also takes the necessary steps. So a lot of necessary steps have already been taken. You know, the power generation has moved gradually from fossil power to renewable power. Transportation is moving from, you know, the fuel to EV, and so many steps are being taken. We know that the carbon emission is dropping with these, but do we know how accurately the numbers are? Are we actually dropping properly? Are we actually reaching towards the number that we are actually targeting? There are so many methods which are available right now. So we could just look at some of what we have seen in some of the developed country for that matter. And since Huga Energy Canada has been our partner in this, we gathered some data from Canada and Germany, and this is what we saw. That when it comes to carbon emission reporting, when the companies were asked about the figures which they had submitted, they could not prove it. Right? They had all said that, okay, we got the carbon emission. None of them could prove it. We found that 24% of 300 Canadian companies actually are victims of ESG fraud in the last 5 years. So that's another fraud that we have been hearing so much about cybersecurity and so on. But this is another fraud which is going to emerge as the pressure on us for carbon emission calculation comes up. These kind of frauds will also emerge. Fortunately, we are at a stage when we can take all the necessary steps to, to de-risk ourselves. But this kind of thing is emerging. 89% stakeholders, they have asked for proof of the ESG records. If we look at some of the figures in Germany, for example, you know, there are 6 different GHG protocols which are prevalent in Germany, and they are all certified, okay, 6 of them. But the result vary as much as 31.5%. Then what do you do? Which is right and which is not right? That's why the calculation of the reduction of carbon emission has become very important. There is an entire industry getting raised on carbon emission reporting systems, which is what is now emerging. You know, so you have emission factors which are used for calculation of this reduction of carbon emissions. If you look at Google, let's say emission factor, let's say emission factor for coal, which is the primary source of fossil power, you will find the range is between 800 to 1000. The question is it 800 or is it 1000 or is it 900? So many, they are all in varying ranges, and there are so many assumptions being made before the calculations actually take place. So therefore, there is a need to have an accurate system to develop or to show the actual numbers for carbon emission here. And why is it that India Power is trying to do this? We are a power distribution company. We supply fossil power, we supply renewable power, And like all distribution companies in India, there's hardly any company which supplies 100% fossil or 100% renewable. Everyone in the course of journey of moving into renewable, they are supplying some percentage of fossil power and some percentage of renewable power. Therefore, it's actually the energy mix which most of us are getting. Now, with this energy mix, do we know that how much of carbon emission we have saved? That's the question that the distribution companies needs to answer, because they are supplying this power. They are supplying the energy mix which is of fossil, which is of renewable. Renewable also are of so many types, and therefore the emission factor of all the types are different. So the onus is on the distribution company to actually tell you that how much of carbon emission you have saved. This is particularly more interesting for manufacturing industries such as steel industries. Today, most of the steel industries are looking to move into green steel production. Green steel production is when you use renewable or green sources to produce that steel, in which power is one of them. And if the power distribution has a renewable component, they would like to know that by taking power from a certain distribution company, how much carbon emission they have saved. And therefore, again, the onus comes on them, and this is particularly coming all from the manufacturing industry. As we all know, the green products are far more marketable than the non-green products. So therefore, the manufacturing industry is actually moving into that direction. In fact, green products are exportable. Okay, there are products which are not exportable only because they are not green. So therefore, the focus has already moved into the carbon emission side in their products, in their production. To ensure this, they need a very clear calculations of why or how much carbon emission they have saved from, let's say, the power industry. So therefore, there is a need then. If that is the need of the manufacturing industry, of the consumers, of so many stakeholders, there is a need for a common energy data exchange, which will have information of various sources of power, renewable, fossil. You may have even among renewables so many various times, and therefore that information should be centrally kept, or at least in an authentic way it has to be kept, and that will leave no room for data manipulation, and it will eliminate the possibility of any kind of carbon emission frauds which are likely to emerge from all these things. Very soon the country will have a law which will mandate various organizations to follow a certain percentage, and then that percentage will be calculated based on established methodology. And that's why it is important that all the industry get the right figures, and that is what we have been focusing on. So in this paper, what we have done, establishing this need here, when India Power and Huga Energy, we joined together, we basically developed a solution here, because most of the consumers, they get their power from the mix of fossil power and renewable power, and and renewable power for that matter, or the energy mix for that matter, is not constant throughout the day. We have more solar during the day and no solar at night, right? So therefore the energy mix is also varying throughout the day. So what is important is to capture this data which is varying throughout the day. Fortunately, we have very established mechanism in the country, which is usually maintained by the SLDC, State Load Dispatch Center, in addition to the distribution companies, using smart meters or IoT devices. And these data are calculated or captured every 15 minutes, which means you have 96 sets of data every day coming from the system, which is coming from the sources of data. Using these 96 set of data per day, we have developed an algorithm which will calculate how much during the day the consumer has saved the power just by utilizing the power from this particular source, which is the distribution company. And this is what has become this solution which we are, offering it now to the consumers, our consumers, and very soon it will be extended to the consumers of other distribution companies who do not have a ready solution available to them. This solution has been patented. It has been applied for patent in both US and Canada, which we have developed, which India Power and Huga Energy have developed together, and we're just expecting the approval shortly. Okay, but this is going to be, it is in the process of getting certified in India as well. Okay, so if we look at the various kind of carbon emissions, we actually are divided into three parts there. There is a scope 1, there is a scope 2, and there is a scope 3 which are part of it. Scope 1 are all referred to the direct emissions from sources owned and controlled by the companies. We have scope 2, which is the indirect emissions. Now, when a power distribution takes from various sources of power, they are classified as an indirect one because they have not generated. They are distributing the power to you. So therefore they are classified in this scope 2. And that is what India Power is also classified. We have generation units also. We have renewable sources also. But our distribution is different from the renewable, different from the generation. So therefore we get classified into scope 2. There is a scope 3 as well, which is all other indirect ones. For example, transportation and other things. If you look at that's called the scope 3. Now we have focused on the scope 2 because that is what our consumers need. And that's what most consumers need who are consumers of the power here. So this is the one which is pending patent right now, which we have developed. We have developed that most accurate way of actually doing this. And giving these results, we will certify to the consumers that what kind of carbon emission they have saved by taking power from us. They need certified ones. We have got requests from some consumers who said, I need 100% power, renewable power from you. We do not want an energy mix. We have got new customers coming with that also. We will certify to them also that how much carbon emission they have set by taking power from us. Okay, so just to tell you, solar energy, most of us think is emission free. Yes, that's true, but at the same time, it's not true 100%. Because if you look at carbon emission in the entire life cycle, it's not carbon emission free because there is a there is a solar panel being developed from minerals and all that, right? There is a transportation involved, there is a cleaning involved, and so on and so forth. And even at the end of the cycle, you have dismantling them, right? So they are not, if you look at the life cycle of the solar, they are not carbon emission free. But if you take the running one, after you have got the infrastructure in place and everything, yes, it is carbon emission free, right? Both wind and solar. We calculate that as well. So we should be able to give this to our consumers and they should be able to use this to their advantage. Okay, so we chose blockchain technology for developing this solution. For obvious reason, I think blockchain is the most trusted solution compared to any database for that matter. Okay, so it has various advantages. I think data integrity is what we are trying to address here, and nothing better than blockchain to address that trust than anything else. So various things like data integrity, regulatory landscape, transparency and auditability, because ultimately the data will be audited by various people whom we are certifying. So, and you cannot delete any data there. You cannot delete anything at all in blockchain technology. That's what the technology is all about. So we chose blockchain to develop this solution, to develop that software based on which this has been selected. And we are offering this solution to the consumers, which is fully auditable. And it will offer a complete transparency and full data integrity that we will ensure, and it is open to any kind of audit by any private or government agencies. Okay, so that is the kind of data integrity solution that we have developed here based on blockchain. Okay, so far we have focused on the scope 2 as we have mentioned, but yes, we are going to go beyond scope 2. We are going to move to scope 1 and scope 3 here. The idea is to extend this to most global use of this platform and making sure that more and more people benefit from here. Not just the consumers of power here, but maybe many of the manufacturing industries, many of the other industries, once we have done in scope 1 and scope 2. But as of now, we are fully ready to offer the solutions to scope 2 here. That's all I had. Thank you very much.
Thanks, Sanjeev. I guess I'm in a very live business problem. Particularly, I mean, I've seen that the point that you mentioned about the 30% inaccuracy or the variance in the calculation of the emissions, right? I mean, and the problem solution, where again the technology is the heart of it, right? The blockchain solution.
Rana, I think I hooked onto one of the words that you said that technology is going to solve the problem. So I'm here to talk about technology, especially in the methane reduction area. And I'm glad that I came after Nicola and basically they talked about measurement and quantification. So what we know is that measurement and quantification leads to abatement, and that's where we come in. So in the logical sequence, I'm here. My introduction, I am from Baker Hughes. I am the product director for flaring reduction technologies. I work in technology development for reduction of methane emissions, and the technology needs to be available now and in the near future so we can reach our goals. So just to start, why methane? I think everyone talks about CO2, everyone has ideas about solar, hydrogen and everything. But if you look at it, methane is what I would call a low-hanging fruit when it comes to decarbonization, right? It is 28 to 30 times more potent than CO2. Whoever depends on who you talk to, which institute you talk about, right? And we have around 120 million tons of methane emissions from fossil fuel industry, direct and indirect emissions from venting, flaring, fugitives, right? And 70% of those come from 9 nations alone. But then even though India is not the biggest producer of methane emissions, there are a fair bit of methane emissions from Indian industry as well. What we also know, and this is where we come in, is that 80 million tons of emissions from methane emissions from fossil fuel industry can actually be reduced from existing technology. It's not something that is TRL 4, 3 that will come 5 years down the line. We can go today and prevent those methane emissions. So my job is to make those technologies available. Sometimes it's just a little bit of customization, so it's an existing technology that's been used somewhere. So I think the new wave of methane regulations, European methane regulations, and OGMP, as Nicola mentioned here, is one of the key drivers, because everyone now realizes how a low-hanging fruit methane is and how we can achieve decarbonization at scale. We are some of the new green projects, we talk about 50,000 tons a year saving of CO2. But with some of the methane abatement, we talk about millions of tons of CO2 equivalent abated a year. So what is flaring exactly? I think oil and gas industry is very familiar with flaring. It is an unnecessary evil, or rather necessary evil, but an unnecessary event that we could, if possible, mitigate. Flaring comes in practically 2 or 3 different forms, what we would call routine flaring, non-routine flaring, and safety flaring. Non-routine and safety flaring is something that I think not a lot of people can do a lot about. It's something that must be done for the safety of the people. But in terms of routine flaring, I think that's where the low-hanging fruit is. A single flare can give us a lot of potential savings. And I think you talked about the methane and the destruction efficiency of methane. We also do calculation with some of our products on destruction efficiency and for assisted or unassisted flares and there. But that's not what I'm going to talk about. I'm talking about the reduction of flaring by itself, not just measurement there. As you know, zero routine flaring by 2030 is a stated goal for World Bank. And I think that's one of the big drivers, but to me that shouldn't have been the driver. Just to reduce the methane should have been by in itself a driver, because today in terms of CO2 abatement, everyone talks about what is your dollar per ton cost of CO2, but with methane, I think most of us are talking to a customer how much money you can make. It's not the cost that you're spending, but how much money you're making by an investment into a methane reduction project. So when we talk about MAC cost or marginal abatement cost of CO2 abatement, with CO2 technologies, hydrogens, and other things, you're talking about how much money you're going to invest and not get back on dollar per CO2 that you abated. But with methane, I'm talking to my customers, yeah, what is your IRR? Is it 15% or 30%? In some cases, 60%, depending upon what they've got on their asset. So, there is process improvement, energy efficiency. I can talk a lot about it all day, but basically, the idea is that methane needs to be reduced. So I just pulled up this chart. This is based on publicly available data on flaring across the globe. And this is just what we call small to medium sized flaring, which we classify between 0 to 50 million standard cubic feet a day. You can see there are, I don't think I can count the number of dots that I have on the map there. And this is only small to medium size. There are large scale flaring globally, and I think Total, we are doing a lot of work with them on the large scale flaring as well. But small to medium scale flaring is the problem area because the big flaring projects get a lot of investment. You've got a bunch of gas. What do you do with the small scale flaring? And flaring has its own problems in terms why it is not monetized or it is attracting that much investment. You have flares in North America, like in shale field, that drive down after 5 years. So you don't want to invest into a project that is maybe after 2 to 5 years, it's going to dry down. But on the other hand, in Middle East, for example, you've got 20, 30 years of assurance that the flare is going to last because we know the field has the oil left for next 20, 30 years. So the flaring is all around the globe. We have few countries like Russia, Iraq, Venezuela, Iran. They are the biggest flarers. But as you can see, India is not devoid of flaring either. We have some flaring in Indian fields as well. And the easiest, again, I keep talking about the low-hanging fruit, but the lowest hanging fruit is the onshore flaring, which happens to be the biggest portion of all the flaring. So going offshore, I think I've talked to a lot of Indian customers, their problem in platform space, availability and all. But in onshore, we really have no excuse. We have the land, we can... The important thing is the technology right? Are we using the right technology that gives you the rate of return on investment to reduce your flaring? So, and that's where we come in as technology company to try and give our customers a product that is applicable and reduce their flaring emissions. We just did some numbers, and again, this is just to give an idea of flavor, not necessarily accurate in terms of what exactly world needs to do, but by reducing small and medium scale flaring alone, we are talking at 25 to 35 gigawatt of power, which is currently going up in flames, right? And this is based on just publicly available world data. This is nothing special. Okay, so I can talk about a lot of flaring technologies, but I think that would be too distracting. So we focus a little bit on let's say the most relevant technology here is to try and generate power out of flaring emissions, or I keep calling flaring, but it's actually associated gas, and as it call in oil and gas field, right? So generating power is somehow the most logical, but the problems till now have been how do we produce power in a right way from a flaring emission? Do we put a gas turbine, a large gas turbine in a difficult place that the flare might die down? And we typically do frame 5s, frame 6s, large heavy duty machines, but they require a certain amount of flare gas, associated gas. So the problem was that you have big gas turbines or you have very small reciprocating gas engines. We are talking 300 kilowatt to 1 megawatt engines, or we are talking 45 megawatt. So that's where the gap in technology was, in my opinion, that we are not talking the right product or the scale of product that would go and solve the problem of what we said, small and medium flaring between 2 and 50 million or 20 million standard cubic feet. So that's where we worked on, and we basically developed some products that can reduce and give value to our customers and reduce their emissions. So what we've done is basically taken our turbine, which was developed for natural gas, and reinvented it to be worked on, to be able to work on flare gas. And flare gas comes in all sizes and all compositions. It's not the same product that you're going from India or North America or Middle East. Everywhere it's different. It's heavy gas. It's mix of methane, butane, propane, and C5. So what we've done is taken that turbine, which was supposed to be, for a natural gas, very clean gas, but we've developed it to work on a very rich gas, so that you can apply it directly on a flaring associated gas stream. And not only that, what we've done is also made it mobile. So if you know that you have an event which is going to last 3 weeks, 5 weeks, sometimes more, and you're going to flare in that time, maybe you can produce power during that time and move that asset again, an asset that can be set up and commissioned within a few days versus a few months and not movable in the past. So we've developed a product that basically helps with the reduction of flaring by generating power for your short-term use, long-term use. As you know, it can be on a trailer, it can also be on a container, so depending upon what your use is. So we've taken the old technology but renewed it to today's needs. So as you can see, this is basically a gas turbine paired with a generator. We manufacture all of it, but traditional application has been, as I said, industrial power. We're using natural gas. Peak shaving is a very fast start and stop machine and bridging power. But what we have recently developed the right use case is to use for flare and e-frac. So oil and gas field operations, if anyone is here, and I'm sure many of you are, that in an oil and gas operations, you are basically having diesel engines, 1 megawatt, 300 kilowatt to 1 megawatt, and you have maybe 50 to 100 in one area alone, these kind of gensets, and you're hauling diesel to bring diesel to site. So instead of, doing that diesel and generating much higher emissions, which is NOx and unburnt hydrocarbons, you could use your own flare gas, which is you are currently wasting, and actually generate power for your oil field operations. So e-fracking, it's actually one of the use cases in US that we are working on, and I've done a case study on that. So by using this gas turbine for your e-fracking, where you were previously using diesel engines, now we are able to reduce emissions by, as you can imagine, by a lot. Basically, your NOx emissions by itself is 90% reduced. You have noise reduction, right, from 100 dBA to 105 to 85, and fuel savings. And what we have noticed is that just by using a gas, and we have compared it with the natural gas price, not even flare gas, which could be negative value per se, but even if you just take a natural gas price versus diesel, we are actually just the investment is giving itself back by getting this product instead of going through a diesel engine. And it has a smaller footprint. Imagine you have 12 to 16 megawatt power that I can give you on one trailer, right? And you need to have like 12 engines out there, diesel engines. You have to connect all of them, do manifold, and then maintain those 12 engines. Your cost is much higher. So by in itself, you are basically financing your own operation and saving cost while reducing your emissions, which is why I said in the beginning that people talk about dollar per CO2 positive. We are talking dollar per CO2 negative. So by these technologies, we can actually do negative marginal abatement cost for emissions reduction. Yeah, and just to give you some numbers, a flare of 5 to 10 million standard cubic feet, if I abate today versus current emission, and I'm taking even assuming 98% efficiency of combustion, which is not necessary globally. They have much lesser. A 10 million standard cubic feet a day flare is, order of magnitude 500,000 tons of CO2 equivalent a year. And it is considered as very medium flare, very standard size. In Iraq, an average size flare is around 8.5 to 9 million standard cubic feet. And we are talking thousands of flares. So one alone can give you 500,000 tons a year reduction. So I think flare is the low-hanging fruit, and I hope the the financials itself will drive the investment in flaring, and our work in developing technology that can be easily deployed and is profitable. So yeah, that's all I have. Thank you so much.
Thank you. Thank you, Mr. Dheeraj. Yeah, that's quite interesting. Quantification and then followed up by monetization of that, whatever is waste, considered to be waste. So yeah, let's move on with the next presentation. We have Mr. Swaminathan from BPCL. So yeah, the theme of this presentation is also about utilization of flare gas recovery, but this time it's in the context of refinery. So over to you, Mr. Swaminathan.
Yeah, yes, sir. In that, I would like to place my sincere thanks to the IEW 2025 and the chair and my concerned BPCL for giving me the opportunity to showcase whatever we have done in the delayed coker unit of the BPCL Bina refinery. Yes, we all know that climate change is nowadays a serious major concern, and why it is a serious concern? Because we have known that greenhouse gases are the major driving force behind that climate change. In India, we can see that around 70% of the energy resources, we can see that greenhouse gases have been emitted. Yes, based on this, and my topic will be in the flare gas recovery, as my fellow speaker also told about that recovery of the flare gases, based on that, how it is the flare gas recovery is integrated in the delayed coker unit. Like that we will see in this presentation. Coming to the insights of the Bina refinery, it is the refinery situated in the central part of India, and the crude comes from the Vadinar through the underground pipeline. It is around 937 kilometers and goes into the Bina. From the Bina, that finished products, we have been dispatching to the Bina dispatch terminal, and then through the product lines are there. Bina Kota pipeline are there, and then Bina Panki pipelines are there. And apart from that, Kandla Gorakhpur, that LPG pipeline is also there. We are also supplying LPG in that. And next, coming to the refinery configuration. Present capacity is around 7.8 MMTPA. In the next 2 years, it will be revamped for another 4 MMTPA. Here that Nelson index, we can see that 11.76. Here we can process the tough crudes. And the secondary processing units, we are having that motor spirit block, that HCU, DHT integrated, and DCU is there. In our CFBC boilers, we have been fully utilizing the pet coke coming from the DCU unit. That indigenous coal, we have stopped it. And based on that, these are the agenda for my session today. The first, why we have to go for that flare recovery, then how it is what innovation we have done in the delayed coker unit, and what are the equipments, what benefits we have achieved, and then how this reliability has been improved. Yes, first of all, why flare gas recovery is required. Here in almost all the refineries and petrochemical units like that, here that flare loss is there. Flare loss is mainly occurs from that some PSVs are passing, like that feed surge drums, that blanketing vessels are there. It has been from there, it can be released. And apart from that, in that we can see that in the blanketing also, we have done that, made that split range controller into a separate controllers with the different set points. By that, we have avoided the flaring going to the flare headers. And in some other units like that, like in MS block also, I'm considering it in Bina refinery, some ISOM unit like that, some dryer valves have been passing. So it cannot be controlled. So it is going to the flare header. And this contains LPG and some amount of naphtha. For this also, we have to recover those valuable products. And this in turn gives a benefit in the fuel and loss, for the business targets also. And then coming for the new projects, whether this flare gas recovery is a compulsion. And then next we will see about that innovation what we have done in the delayed coker unit. Here we are having that in delayed coker unit, 3 coke drums are there. This is the unique in the country. And apart from that, for that coke drum warm up, heating of the coke drum for every 24 hours, like 4 hours we have been utilized this ring compressor for warm up. And apart from that, next 20 hours it used to be idle. It was based on that, it came into the revamp of that unit. And due to that brainstorming, we have done in the next 20 hours, how we can use that period for utilizing the flare gas recovery. For that, we have approached our PMC and process licensor also for integrating this ring compressor with the flare header. And that process licensor, and they have told that this is the unique case. We have not done any such in the country like that. And apart from that, we have repeatedly insisted on them to do this project for us. Based on our requirement, they have considered this is the CLG Lummus, and they have integrated the flare gas recovery into the delayed coker unit also. Presently, we are having the dual purpose. One for that heating of the coke drum, and another for the recovering of the flare gases. Here, this is that this flare gas recovery is this is a low capex item. It costs around only 5 crores like that. When we go for a high intensity flare gas recovery, it will cost around more than 40 crores. In that, like the HT motor involvement will be there. So we have avoided in going for that. Since our refinery is a mature refinery, that flaring will be in the minimum quantity. And this ring compressor caters for absorbing this flare gas recovery. And apart from that, in the last one, I have told that here that based on that the flare gas, we have been recovering that LPG and naphtha. For that, in a year, around 10,000 tons of LPG we have recovered, and naphtha around 5,000 tons we have recovered. And this is a low capacity that ring compressor. Here we can see that picture of the water ring compressor. This plot area is very less. It will be around 52 meter square area. In that, it can be accommodated. Here on the right side, we can see that 2 dual sections are there. One from the flare gas header and another from that blow down tower. It is coming from the coke drum. Here we can see this is the schematic of the water ring compressor, how it is integrated with the refinery flare header and delayed coker unit. Here from the in process units, we are having the flare header. After the KOD, this flare headers goes into the refinery flare KOD, and then it goes into the flare stack here. From the main header, we have taken a tapping like that, and then it goes into the liquid ring compressor. From here, this liquid ring compressor is around a 90 kilowatt motor. This is the Gardner Denver make is there. Its capacity is around 1.4 tons per hour. Yes, and then apart from that, it can take suction from the vacuum also. It will be the pressure around minus 0.12 up to it can go up to 0.83 in our case. This is for the low capacity that ring compressor. And apart from that, this ring compressor discharges these gases to the water ring compressor. Here we are having a water ring compressor. In that, it will go into this water ring compressor, sucks those liquid ring compressor gases, and then we have been putting it into the vapor recovery section. In the vapor recovery section, that LPG, naphtha, and LCGO, like that, it can be recovered there. Here also, in day by day, in years, we have faced more problems like that. Earlier, that ring compressor discharge was connected with the both going to the water ring compressor and the discharge header. And then because of that, that machine used to trip continuously. So, and then we have bifurcated the line like that. And coming to that benefits we have achieved, in the benefits, this investment is around 5.47 crores. Here we can see that payback is less than 3 months. And then that flare recovery, that it is operating around more than 97% in a month. Here that yellow, in the second graph you can see that yellow bar, and these are the carbon emissions which have been recovered for the year wise. In 2022, like 4,000, and the next year it is around 7,000, and in the next year around 12,000, like that we have been recovering it. And the red line shows how much it is impacting our fuel and loss percent is there. Since it is a small capacity machine, it is around maximum, it can go up to 0.17% like that. Here we can see that ring compressor on the month-wise flaring. Here for a month, we can see around only 3 tons flaring we can see. And the rest, we can see that this is a nil flaring. And in the blue lines, it shows around the recovery, how much it has been recovered from the main flare header. It is almost more than 97% that recovery is there. And I have considered this only for the non-emergency flaring. And for that shutdown period, this has been excluded. Here I am coming to the reliability improvement. As I have told that the DCU flare header, here earlier that pressure has been kept around 0 kg. In that, while we took suction from the flare header, the machine used to get tripped. For that, based on that, we have discussed with the licensor, and we have changed the trip values to around minus 0.1 kg. And apart from that, in the flare header also, we have taken a pressure tapping around 100 mm WC. In case it should not suck the vacuum or air from the flare header. So additional interlock has been provided. Here the second point is the discharge pressure high. The machine used to get stripped out. For that, in the revamp, after that revamp, we have made a separate line. It goes into that water ring compressor. By means of that, we have eliminated the tripping also. And in Bina, we can see that peak summer, it goes around 50 degree. In the 50 degree, this sealing temperature is there. For the in liquid ring pump, that seal water has been maintained. It has been in circulated condition. For that, this temperature used to increase. It will go up to 44 degree. The machine used to trip. For that also, next we approached with the OEM, and they have told that we can go up to 50 degree. Then we on the safer value, we have put around 49 degree, and this also we have eliminated. Like that, and another one from the blowdown overhead vessel, that liquid used to carry over, and this with the coke fines, it will get stuck in the separator LT, and this LTs used to get malfunction. Like that, it will go up to high level, it used to trip like that. And based on that troubleshooting, we have identified why that oil carryover is there, and we have eliminated that one. Based on that also, this has been rectified. And the last one is that if we go for that separator LT draining, here the DCU contains more than around 18% H2S is there. It will be harmful for the persons working for that. So we have avoided it by putting it to the closed blowdown system. Yes, and then in the conclusion, we can see this is a low capex, low opex project, since it cost around only 5 crores, and that for the last 5 years, this machine has been in operation, and there is no such major cost like that. Here, there is no such moving, it is a wear and tear. There is no such wear and tear. And it can be replicated in other compressors also, like in hydrogen unit, that fuel gas compressor, it can be hooked up in the fuel gas compressor like that. Or if any other compressor, any margins are there, then we can also put it like that. Here, this also minimizes the flaring, and this fuel and loss of that concern is coming around like 6.7. It is our target. We are meeting. We are going less than 6.7 also, the business plan targets. And as I told that it recovers the waste gas, and it also converts it into we are separating LPG and then diesel also from there. And last, it is our duty, we have to realize what that carbon footprints, whatever activities we are doing, we have to analyze why these carbon emissions are happening, and we have to control it. And this perfectly fits into that India's climate action plan, that is a Panch Amrit policy is there, and it is perfectly fitting in that. So this is all about that water ring compressor from the delayed coker unit. Thank you.
Thanks a lot, Mr. Swaminathan. Great to see that the technology solution, is having a payback period of less than 3 months, right? So that was great to see. And I guess one of the important point is that it actually reduces or rather consumes, the non-routine flaring, about the same. And moving on to Anshuman, because the previous two discussions were more about how to abate the flaring. But at the same time, what Anshuman is going to talk about is that how to actually not arrive at that place, right? How to actually reduce the non-routine flaring out of a particular technology solution. Please, Anshuman.
Good afternoon, everyone. Thank you to the chair for such generous introductions. It's really an honor to be included in such a distinguished set of
Good
panelists.
afternoon, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the halls. Please take care of your belongings. Thank you.
Yeah, so I was saying that it's really a privilege to be included in such a distinguished set of co-panelists, and thanks to the organizers for bringing us all together, and to the audience for their patience. So I'm not going to take much of your time. I'm just, there has been so much talk by Mr. Dheeraj also of flaring reduction and how it is a low-hanging fruit. So my presentation is just going to be an effort of how we can pluck that fruit if from the process side, as I'm an operations guy. So I'm going to talk about the processes that are involved in a startup of a steam cracker plant. And as it was said, that flaring is a necessary evil. So sometimes we have to flare some of the gases that we use in the processes, and during startup time, it becomes sort of, when we don't achieve the optimal temperatures or the pressures, we have to flare the impurified product to the flare headers, and all such schemes have been developed that sort of talk about reducing flaring, but not from the process or scheme side. We have so much of talk about greenhouse gas emissions and Panchamrit goals. So to achieve those, we sort of start if we start from the process side, it becomes easier for us to eliminate these emissions. So my presentation is going to be divided into 3 sections. First section is just going to be a brief overview of what a steam cracker plant entails, a process flow diagram. And the second is what is the conventional way, what is the conventional form that we use during the startup, what are the procedures that we use during the startup. And the third is the modification that we are proposing that sort of reduces, or we hope that it completely eliminates flaring, but it sort of reduces the flaring. So let's start. So what is a steam cracker operation? It's nothing. It's if we take hydrocarbons, and we have saturated hydrocarbons or naphtha. Now naphtha is all the carbons that from the C5 to C11 carbon chains, whatever we have. So if we take them to a furnace and place them in the presence of steam at high temperatures, they break and form ethylene and propylene or other unsaturated hydrocarbons. So in the petrochemical industry, the main raw materials to start making petrochemicals are polyethylene and polypropylene is ethylene and propylene. So we need that kind of unsaturation in hydrocarbon chains. Free radical mechanisms and sort of things are achieved in furnaces, and steam cracking operation is thus important because any petrochemical plant has its mother unit as a cracker, as a gas cracker or a naphtha cracker. It depends upon the feedstock. So these reactions require a residual time of less than 1 second and are endothermic. It's just at the risk of sounding a chemical 101 class, but these are some concepts that are basic chemistry, that if we, for example, we take ethane and we crack it in a pyrolysis furnace, we get ethylene and we get hydrogen. So one more important thing that I would like to mention here is that every cracking operation has or will have hydrogen as a byproduct. We cannot eliminate that. Any free radical mechanism involves hydrogen, as hydrogen radical is the most reactive, and it reacts perfectly with itself. So we'll have hydrogen, and I will show you, I will tell you in the coming slides why hydrogen becomes a sort of problem for us, because we need to separate it methane, and for methane separation of hydrogen, we need a temperature of minus 165 degrees Celsius, which is extremely cryogenic. So thermal cracking involves fired heaters and then hot end removals, all the products that are achieved after cracking, which are heavy end separation, separation of fuel gas, separation of fuel oil, and compression and product recovery. Now in a conventional refinery, we have heaviers and we have lighters. So we have normal distillation columns that operate on the basic principle that you reboil and then you condense. When you reboil, you get lighters, you condense them, you get, from the top you get lighter products, and from the bottom you get heavier products. But in a petrochemical plant, or when we are sort of trying to achieve ethylene and propylene, there are only lighter ends. Everything is light. I mean, if we talk about heavy ends, we have crude oil that have carbon chains ranging from C220 to 240. But only in our naphtha cracker plant, the feedstock is C5 to C11. Only 5 carbon chains or 11 carbon chains. And then we are breaking them too. So we are getting C2s, C3s, and C4s, which are at normal temperature and pressure. They are gases, they are vapors. So you cannot use a conventional distillation column which includes just reboiling and condensing, because it is not going to achieve anything. So for that we need compression. Like, it's basic that if you want to condense something that is uncondensable, either you reduce the temperature or increase the pressure. So we are doing both. We are increasing the pressure and reducing the temperature too. So we have compression, high pressure required to fractionate light gases from heater effluents, and then we have the product columns, because every distillation column in the naphtha cracker or the steam cracker plants, it operates at heavy high pressures. So this is a flow diagram of the naphtha process. It's a basic diagram that we have naphtha, we have furnace cracking, temperatures in the furnace reach 1100 degrees Celsius, we have fractionator columns, we have quench tower, we need to recover that waste heat that we have, and then we have the CGC, charge gas compressor. All the material that has been cracked in the furnaces and has been converted from liquid to gases or from gases to gases, that gas is called charge gas. It's laden, it's charged with ethylene and propylene, but it also has many impurities. And for that, and now we have the chilling train. So before the chilling train, we have a dryer. So chilling train has cryogenic temperatures, so we need a dryer because we cannot afford any H2O in our process. A dryer, it will just solidify and choke all the plant parameters. And then we have DM column, demethanizer, deethanizer, ethylene fractionators, PF, DPs. Now, if any column has D prefixed to it, it means that it's going to extract those carbon chains. Like if we have demethanizer, it's going to take all the C1s at the top. If we have deethanizer, it's going to take all the C2s from the top. And then if we have DP, it's going to take all the C3s from the top. Now C1s include ethylene, ethane, C1s include methane, C3s include propylene, MAPD. So as per the requirement of the downstream sections and the petrochemical plants and the polymer plants, we need extra high purity ethylene and propylene. So that is achieved in fractionator columns, ethylene fractionator. Ethylene fractionator is basically just, you get ethylene from the top and you get ethane from the bottom. These are the basic distillation columns. And acetylene converter, you convert the 3 bonded hydrocarbons with reacting with the hydrogen, and then you get ethane and ethylene. Now the point here is that you see that from the top of DM we are getting methane. This same methane is used as fuel gas in the furnace, so it is a highly integrative, heat integrative process. You are taking the ethane and methane that you are getting and you are using it in the furnace to crack the feed that you are getting. So it becomes a highly integrated process, but it is a process when it is running. This integration is only achieved when we have achieved a sort of feed running of 20 to 24 hours. So its normal startup procedure looks like, I'll just show you this slide. If we start up a plant, we don't have anything. We don't have methane fuel gas because we are yet to extract it. So we have to take utilities and extra gases, fuel gases from the top. So all the utilities and fuel gas systems are charged. All the compressors and refrigerant compressors are charged. Ethylene, propylene fractionators, we take inventory from the EF and PF and from battery limit, and we run them on total reflux. And heaters are cracked to produce the charge gas and replace the nitrogen in CGC. So it is sort of a technical, it may sound a bit technical, but it's simple, that I am running my columns on total reflux. Total reflux means I am not taking any product, I am not taking any feed, I have just taken some inventory, I am reboiling it, I am condensing it, I am giving it back to the column. No forward flow is achieved. So some columns are in a normal steam cracking operation, in a normal startup procedure. Some columns are run on total reflux, and before any feedstock or any other such utilities are taken in line. And only after the cryogenic stabilization of the columns is achieved that we sort of start extracting the product. Now what is cryogenic stabilization or cold box stabilization? It's just that to achieve -1, now I told you that we have hydrogen and methane. To separate our last end products, we cannot have so much impure methane that it has 5% or 10% hydrogen, because if we use it in burners, it causes knocking. we have to use that methane in our furnaces. I cannot just say that I have extracted methane from the demethylizer column, and now I can use it, I can give it, I can sell it to other purifiers and other units that will purify it. I am using my own methane, so I need it purified. So I need to extract hydrogen from methane. And for that, even at high pressures, including 35-40 kg pressures, you need a minimum temperature of -165. So I need to have a cold box. A cold box is just a brazed aluminum type of heat exchanger, split type heat exchanger that sort of has -165 degree temperature reaching, and it separates the hydrogen from the methane. Now this achievement of temperature in cold box takes 12 hours or 14 hours or 16 hours, depending upon the operation conditions, but it is time-taking process. And till the time I have not reached those temperatures in the cold box, I cannot extract products. So I need to flare all those products during the startup of the cracker plant. I'm getting impure products, I'm getting impure, I cannot use them anywhere. Polymer plant needs high accuracy, high purified ethylene and propylene. They cannot even afford 1% acetylene in ethylene. That's why acetylene converter was there. And I'm getting 10% acetylene in ethylene during the startup. So I'm flaring all those products, and it's just causing a chaos, but it's the normal startup procedure that is followed throughout the globe. So this is the normal startup process flow diagram. If you see that I'm not getting any methane. DM column does not have anything from the top. I have started the flaring from the exchangers and the cold box itself in the upstream sections, and even from the CDC sections. And I'm taking RLNG, regasified liquefied natural gas, from OSBL to crack the furnaces and take the feed. So 180 to 200 tons per hour of feed is being flared for 12 to 13 hours. So it becomes a highly wasting process, and it is not we cannot say it is an optimizable process, but a scheme we thought that we should develop and we should follow through is that the two major questions that we need to answer here is why flaring of gas is required and why can't the amount of flaring be reduced. Now we have to flare because we are getting impurified products, and why can't the flared gas be decreased? Because actually if we have a compressed gas and we depressurize it, so we have something called a Joule-Thomson effect. So if you depressurize a gas suddenly, it decreases its temperature. So actually that's how we are getting the cryogenic temperatures in the end, because we are compressing the gas to 35 kg per centimeter square, and then we are flashing it suddenly to 6 kg per centimeter square. So we are getting that cryogenation from the flaring of and the flashing of the gas itself. So flaring is actually beneficial for us. But we have proposed a method, and it's still in the beginning phases of simulations, so that we can say that we have actually developed an artificial charge gas. So it entails that as I mentioned, we have taken the inventory in ethylene and propylene fractionator beforehand, and they are running on total reflux. Now, those products are pure. I don't need to crack the heaters now. I can just compose an artificial charge gas that is sort of concurrent with the real charge gas that we have, which is 40% methane, 20% ethylene, 40% ethylene, and 20% propylene. Because we are exploiting the fact that ethylene and propylene inventory is available to us prior to cold box stabilization. Now, with the problem with the impure products was that we were not only getting ethylene, propylene, we were getting acetylene, we were getting C5s, we were getting PFOs, and we cannot use them in the downstream sections. So we had to flare them. But if we take a charge gas that is pure, that is only methane, ethylene, and propylene, so my downstream section from the cold box is designed for that. So the specific charge gas composition is chosen for two reasons. This composition is similar to the normal charge gas, and it contains all the major components of the downstream gas. This helps us commission the downstream section simultaneously with cold box stabilization, which is not the current scheme of startup. First we need to flare, and then we commission the downstream. Now we have the purified product, which we processed when the plant was running. So we have that storage capacity in the OSBL sections. So the modified startup procedure is just a simple thing. You take all the utilities in charge, like we took in the conventional way. Now what we do, for the RLNG that was going in the heaters to crack the heaters, now we are not going to take heaters in line. We are going to take the RLNG directly to the compressors. And EF and PF, which were already running on total reflux, we had the inventory of ethylene and propylene vapors. We are just going to make a line. It's going to go to the quench tower or the compressor, and we'll have an artificial charge gas that will just recirculate through the system till the time it flashes and it provides us with those cryogenic temperatures. So the cycle continues, like first compression, flashing, fractionation, again compression, fractionation, and again compression. So this sort of recirculation of the artificial charge gas, not completely, but sort of reduces the flaring requirement we have. It reduces it gigantically because we'll see the cost benefit analysis. Some simulations of initial phases we have started to run. The naphtha we have saved is 150 ton per hour. We didn't crack any fresh feed. We didn't use anything. We just took them from the inventory. So naphtha is saved. Minimum time saved. We don't need time for cryogenation or flaring. 8 hours of flaring saved. Operational cost efficiency. The current price of naphtha is 54,000 per ton. And also the temporal benefit. We are saving time because first we had to stabilize the cold box and then commission the downstream sections. Now we are just simultaneously stabilizing the cold box also and taking the fractionation column in line. And 6,000 tons of equivalent CO2 also has been, like from initial estimates, in line with the Panchamrit goals of the government. We are saving 6,000 tons of equivalent CO2 emissions. So it sort of helps us in achieving all these things. Like efficiency becomes the main motto here from the process side. And this is what an operations guy thinks about. This is from the perspective of operations. So this is from my side. Thank you.
Thank you. Thank you. An excellent presentation. Thinking about avoidance of emissions altogether by some out-of-box thinking, like going into very minute details of the process that exists. And so from the entirety, the key takeaway that I have from this panel is that twofolds. One, it reinforces our view that you can control what you can quantify. So that's one very important aspect that we need to quantify, we need to measure. And we can deploy some very unique emerging technologies like drones, like blockchain for doing that. And then secondly, combining the existing technologies with these new emerging technologies gives us a more effective solution to not only utilize and monetize, but also to avoid emissions altogether. So that's a very good takeaway, I guess, from me. I guess, Mr. Rawat, you might have some views.
No, sure. I think, I couldn't agree more. It is more about, first of all, abating it. And of course, tracking it. And the last point on the blockchain side of solution was quite unique one, because as we actually track it, abate it, at the end of the day, we have to monetize it. Given the carbon markets are coming to India, it would be an interesting one to watch out. Thank you. Thanks a lot.
Certainly. Thank you once again for the excellent panel. Let's give them a very big hand and continue.